mprotect call, because mprotect, which is what we want to call to set things executable. We need to call it with an address, a length, and a protection value that we want to contain at least prot exec. A little bit of searching for useful patterns with some grep finds us this interesting function, IO port readl thunk. Again, what this is actually supposed to do, totally irrelevant. But it takes two arguments, which again we control, and then it follows some function pointers to call it. So we control those function pointers to call it on an address we control, with a size that we control, with a third argument that just conveniently happens to be equal to prot exec. So it will set that memory executable. All right, so to put the steps together, we need to allocate a fake IO range op struct, which is that operation structure. We need to set the read op to mprotect. We need to allocate an IO range object that needs to be page aligned because we're going to call mprotect on it. And it has ops pointing at fake ops, and base is set up such that that adder minus IO port base computation yields a useful length. And then we're going to copy our shellcode into that same page immediately following the IO range. And then we'll do this timer chain. We'll call CPU out L to set the second argument register to 0, because that happens to be a value that makes IO port read, IO port write up here harmless. And then we do this IO port read L thunk, which through this hilarious chain of indirection will result in an mprotect. And then we'll just jump right into that fake IO port +1, which is where we stuck our shellcode. All right. And so that works. Turn off ASLR, code up all the offsets right, and you've got code execution. And so one question before we jump into getting by ASLR is, why didn't I use ROP? Return-oriented programming is a standard, well-understood technique that is the standard way to write these exploits. Why did I do this more creative thing? There's a couple of reasons. One is that this mechanism makes continuing execution getting the QEMU KVM process to continue executing dead simple, because we're not corrupting the stack, we're not really smashing any state, we're just sort of hijacking the legitimate functionality of the run loop. And so after all of this returns, everything is actually, except for the things that we freed as a result of our exploit, everything is in a sane state and we can just continue executing. Another thing that I like about this technique is that I've shown you virtually no assembly on the previous few slides. I've referred to one detail, but there's very little dependence on how these functions actually got compiled. And ROP cares very deeply about how the functions got compiled, because you're chaining together strings of assembly. When you're exploiting a program under Linux, you have to deal with the fact that every Linux vendor has their own build of the program with a slightly different source version, a slightly different GCC version, a slightly different set of flags. And so if you want to have to try to find ROP gadgets across every single one, it's a fair amount of work, and there aren't yet great tools for doing this in a completely automated fashion on Linux. Whereas here, I just need to look at the source, and then I just need to grab the symbol table from all of those different versions, and I have all of the addresses I need, because they're just functions that exist in the C code, and so are more or less preserved across compilation by different versions. And then finally, the cop-out answer is that I'm just personally not that good at ROP. I don't know great tools for doing it on Linux, and so I decided to try something different. All right, so we've got code execution, but I've been assuming no ASLR. So let's get rid of that restriction. So we need two addresses. There's sort of fundamentally two addresses that we've been using. One is the base address of the QEMU KVM binary. If we assume we're attacking a known binary, we know the layout of all of the functions in memory, and so we know their offsets from the executable base, but we need to know where that executable is loaded. And secondly, we need to know the address of that physical memory mapping inside QEMU KVM in order to get the address of fake objects we're injecting. So there's a couple of answers here. The classic answer is find a sufficiently powerful information leak that lets us leak the contents of pointers or the contents of memory and backsolve or backderive somehow these addresses from leaked information. That's a classic way of doing this. I didn't end up going that way. I decided to do, again, something else that I think is a little more informative and interesting. The second option is we can take advantage of the fact that every major distribution still compiles KVM as non-PIE, not as a position-independent executable. If you're not familiar with implementation of address-based randomization, what this ends up meaning is that the QEMU KVM actual core ELF binary is loaded at a fixed address every time. It's always loaded at the same address in memory. And so addresses in the binary itself are not subject to randomization, and we can assume that we know them. So we can just assume that we know for a given binary all of those code addresses. And that means that the only thing we have left to find is the FISMEM base address. To do that, we're going to use yet another obscure feature of QEMU KVM that comes in handy here. There's this FWCFG for firmware configuration subsystem in QEMU KVM. It's sort of a virtual device. It emulates 2 I/O ports. You're not supposed to know or care about it because it's used by QEMU's BIOS to communicate with the emulated hardware. But it's just listening on I/O ports. There's no reason other software that's not the BIOS can't talk to it. Its purpose is to export data tables that the BIOS needs, such as the E820 map that describes the layout of physical memory, the ACP tables that describe how to interface with the emulated ACP hardware, etc. It also has support for the BIOS feeding information back to the emulated hardware. This is a little odd in that, as of the versions that I checked, this support for writable tables isn't actually used anywhere in QEMU KVM. There are actually no place that it exports tables that the BIOS is expected to write. But the infrastructure is there, and not only is it there, it actually lets the BIOS or any software write to any of these exporting tables. And conveniently, several of these tables are backed by statically allocated buffers inside the host. Which means, again, assuming no PIE, they're loaded as part of the ELF binary at fixed addresses, which means that we can write to them and we get nearly 500 bytes of writable data at a fixed, static, predictable address, even under ASLR. So that's enough that we can inject our fake timers, our fake structures into that space rather than into the backing memory map. There's one complication, which is that mprotect, as I mentioned, needs a page-aligned address. And so a 500-byte region is not likely to land on a page-aligned address if it's allocated, if it's at a random offset, which it basically is. So what we actually need to do is or what I did at least, is we construct a different set of fake timer chains using the same techniques that does basically a read 4. It reads 4 bytes at an address we choose from the guest, and then it writes it to a space, or from the host process, and it writes it to a space that's visible to the guest. And so we use that read 4 basically as an information leak. We build up our own information leak, and we chase pointers using those reads to derive the value of that physical memory base map. Once we've found the address of that mapping, we proceed exactly as before. There's a little bit of complexity here, is that now this means we actually need to do that read 4, then do computation based on the results of that read, and then execute more gadgets in the host. So rather than ending our timer chains with next equals null, we actually end them with another timer that calls that RTC update second function again, which, remember, it follows pointers to find a timer and then schedules that timer at 1 second in the future. So we execute this chain, we do the read 4, and then 1 second from now, a timer that we control will again get executed. But until then, the host returns to the guest context. The guest can do arithmetic, do computation, glue bits together based on that read, and then 1 second later, we'll jump back into another set of gadgets. And so we use this to chain multiple timer chains, one after another, with guest execution in between. And so that, then, is what it takes to, or at least the steps that I took, and the broad steps, what it takes to make this exploit work against ASLR, bypassing non-executable pages, and work completely on a stock install of KVM from a vendor. And we'll demo that in just a moment. So before we get to the demo, so that I can end the talk on the high note with the demo, we'll talk about a couple of conclusions that I think are thoughts that are raised by this work. One thing I want to emphasize that I hope this work emphasizes is that virtual machine breakouts aren't magical at all. I think there's often a tendency, virtual machines are kind of magic, honestly. They do this weird thing where you get multiple computers in one computer, and they do that by doing lots of crazy low-level hardware and software tricks to make it possible. And so people tend to assume that attacking virtual machines must be at least as complicated as writing one in the first place, and so therefore they're probably a pretty strong security layer. But that's just not true. All of the usual software protections, ASLR, NX, etc., apply to virtual machines, but that's about it. Virtual machine breakouts typically are memory corruption bugs like any other bugs, and frankly, today I would prefer to be attacking a virtual machine than a modern web browser, because the state of mitigating exploits and defending against exploits and sandboxing is much more advanced there. And so virtual machines, don't think of them as magic security boxes. They're just as vulnerable as anything else, and of course, as you might expect, the fake devices are the weak spot. And just sort of to drive this point home and to give some context, we'll take a brief look at some past virtual machine breakouts. In 2008, Invisible Things Lab put out this paper, Adventures with a Certain Zen Vulnerability, where they demonstrated a Zen breakout. The bug that they were exploiting was an integer overflow in the paravirtual frame buffer, and they did much the same standard tricks that I did, ret to libc or return-oriented programming to mprotect, to copy a buffer in and then jump into it. Immunity at Black Hat 2009 presented Cloudburst, a breakout exploit for VMware. Again, missing bounds checking in the virtual SVGA device, get memory corruption, entirely same techniques. And then just to give a sense of where virtual machines can get interesting, just earlier this year, Invisible Things Lab again put out another attack against Zen, but this one based on a bug in the way that Zen uses Intel's VTD, which is the I/O MMU and hardware I/O protection technology. It turns out that turns out that there was a subtle bug in the way that interrupts were handled that actually allowed a guest to escape. And so that's an example of the kind of thing I was talking about might be possible with the KVM AMD and KVM Intel modules, is that these things are complicated and there probably are subtle attacks that involve the hardware interaction. But once again, the actual primitive that they got out of that attack was memory corruption in the host. And so from there they proceeded in exactly the same set of techniques that everyone else uses for exploiting memory corruption bugs. And so virtual machines are interesting, but they're not that much more interesting. They're not that much more secure than anything else. So that's some conclusions. Some further work that I want to see done and that I'm going to be pursuing is in hardening KVM. The first takeaway is that you absolutely should be sandboxing QEMU KVM if you're running it in a production environment. Fortunately, if you're running it at least under Ubuntu or Red Hat, via libvirt, they are already sandboxing it using SELinux and AppArmor. And I haven't yet, but I want to take a look at those sandboxes and see how hard they are. But this is work that people do realize needs to be done. But if any of you are deploying KVM, make sure KVM in a remotely possibly sensitive context, make sure that you're using a technology that gives you that sandboxing. I think another no-brainer is I'd like to see the distributions start building QEMU KVM as PIE, as full position independent. The traditional reason not to do this is performance, because it costs an extra register to build as PIE. But virtually no one is running KVM on 32-bit platforms anymore, and AMD 64 has enough registers that the performance impact is rarely negligible. I haven't done benchmarks on KVM. It's also on my to-do list. But I think that's an obvious thing that will improve the state of the world. Then we can try some crazier ideas. We could try, to make things a little bit harder, the standard technique of, XOR encoding key function pointers, XORing them with some constant value that's stored at some address, and then un-XORing them when you get them out, so that if a memory corruption bug tries to